4.5 billion years ago, the disk surrounding the newborn sun gave rise to three such distinct worlds: Mercury, Venus, and Earth. Let's rewind to the first spark at the core of a collapsing cloud, the origins of the inner planets. And if you trace it back to the very start, you'll discover something truly enchanting. You need to picture the sun, not as we know it today, of course, but as the sun in its infancy, just beginning to ignite amid this immense swirling cloud of gas and dust. It's called a molecular cloud. Under gravity's pull, it starts to contract, and somewhere in that contraction, the sun ignites. But what remains around it? It doesn't just vanish. Naturally, a disk forms, this incredibly thin, scorching, and turbulent disk of material known as a protoplanetary disk. And right here in this crucible, in this forge of creation, the building blocks of planets start to take form, but conditions aren't uniform everywhere, and that's crucial. The temperature gradient across the entire disk is immense. Near the sun, it's blisteringly hot. So hot, in fact, that only the most resilient materials like metals and silicate rocks can stay solid. Everything with a lower boiling point, ices, volatiles, even water, simply evaporates. They're pushed outward. Thus, the inner planets, those born in this hottest zone, are primarily composed of metal and stone. That's why Mercury, Venus, and Earth are dense terrestrial worlds. They lacked access to the ices and gases that would later form the giants farther out. And this distinction, this divide, is established from the outset. Before we proceed, allow me to ask you to subscribe to the channel and give it a like. My goal is straightforward: to help you fall asleep while delving into the marvels of science. It costs you nothing, but it supports me greatly in this endeavor to share knowledge. So let's continue. The process itself, accretion as it's termed, is captivating. It begins with grains, microscopic particles of dust, and minerals swirling in the disk. They start to adhere. Initially it's electrostatic, nothing more. Tiny particles simply collide and stick, forming aggregates, lumps, and over thousands, perhaps millions of years. These clusters grow. They crash, they merge. Eventually, kilometer-sized bodies emerge, planetesimals as we call them. From there, things speed up because once mass is present, gravity kicks in and it takes control. These planetesimals collide, often brutally, and form embryos, protoplanets, and it's a disorderly process, chaotic. There's no real order. Not entirely. Collisions, mergers, fragmentation, objects scattered inward or ejected from the system altogether. But gradually, through all that aggression and clamor, the inner planets begin to take shape. It's worth noting that all this unfolds on a canvas that's constantly evolving. The young sun is developing. It's emitting a powerful solar wind, far stronger than today's, gradually clearing the gas. And this imposes a time limit on planetary formation. The gas doesn't linger forever. So the material destined to become Mercury, Venus, and Earth had to coalesce swiftly before being swept away. Now, closer to the sun, in the very furnace, we believe Mercury formed. And the reason this is intriguing is that Mercury seems odd. It's very small, naturally, the smallest of the inners, but its core is gigantic, mostly iron, which sparks several hypotheses. Some propose it originated from metallic material right from the start, which is plausible, but others, and I find this compelling, suggest it was once larger and endured a catastrophic impact in the early days. Something so devastating that a significant portion of its rocky mantle was simply blasted away, leaving the iron core behind. Meanwhile, Venus and Earth formed a bit farther out. Not too far, mind you, just slightly cooler, Still hot, still in the domain of rocks and metals, but not quite as extreme. And their composition mirrors that. They're similar in size, mass, and likely in their initial chemical composition. But once again, the details, the history of impacts, the timing of formation, the presence or absence of volatiles, start to differentiate them. Water is the key, not just for life, of course, but for geology, climate, atmosphere. It's believed that although the inner disk was too hot for water to condense directly, these young worlds could have acquired it later via bombardment from icy bodies, comets, or hydrated asteroids from deeper in the solar system. These deliveries might have been irregular, chaotic, but essential. And all of this isn't a smooth process. It's brutal. Planetary embryos slam into each other at tens of kilometers per second, carving craters hundreds of kilometers wide, vaporizing rock, melting crusts, reshaping entire worlds in an instant. Yet through the chaos, a kind of order emerges. Mercury, the smallest and densest, clinging to the Sun, Venus, Earth, and eventually Mars. Though Mars is different, possibly an abandoned embryo that never grew to full planetary size. But that's a tale for another time. What's fascinating about this phase, this early phase, is that it's invisible now. You can't observe it directly. Naturally, all evidence has been overwritten by time. But you can model it, run simulations, examine meteorites, some older than Earth itself, these fragments of planetesimals that never became full planets. And in those samples, you find isotopes, tiny chemical clocks that reveal the timing of these events. Some form just 1,000,000 years after the first solids condensed, which in cosmic terms is a mere instant. The whole thing happens rapidly, yet it lays the groundwork for everything. And when you truly reflect on it, it's astonishing, because all the complexity that follows, tectonics, oceans, atmospheres, life, rests on this moment, on this brief early epoch when the solar system's architecture was defined. And it wasn't guaranteed, not at all. A slight shift in temperature, material distribution, a different collision here or there, and the outcome could have been entirely different. Even today, we see signs of that uncertainty. The moon, for instance, formed from a colossal impact between the young Earth and a Mars-sized body called Theia, a random, chaotic event. And without it, Earth would be different, perhaps uninhabitable, perhaps lifeless. So this phase, the first tens of millions of years, is the most critical, not because it's full of life or beauty, but because it sets the stage. It defines what's possible. And really, all of it boils down to dust and rock spiraling around a newborn star, colliding, adhering, growing, a dance of chaos and chance that somehow leads to planets. There's something hauntingly captivating about Mercury. Looking at it now, this little world, the smallest of all, closest to the sun, and yet it's not just small, it's peculiar, and it's easy to overlook. In fact, people discuss Venus with its hellish atmosphere, or Mars with its potential for life, or Earth, of course, but Mercury doesn't get much attention, and yet in many ways it preserves the memory of a vanished era, like a fossilized relic of the earliest planetary processes. What's striking, and I think we touched on this earlier, but it's worth delving deeper, is just how massive its core is relative to its size. It occupies about 85% of the planet's radius. Extraordinary. For comparison, Earth's core is only about half the planet's radius, so you've got this small, rocky world with an oversized metallic heart. And the question is why? There's a theory that it was always like that. Perhaps being so close to the sun, the solar wind, or the high-energy environment somehow stripped away the lighter outer material, early on. But that's challenging because you'd need an enormous amount of energy to do that, to peel off a planet's rocky mantle. So the more likely explanation is a collision, a giant impact, possibly several. Imagine Mercury as a larger Earth-like object at the dawn of its history, and then sometime in those chaotic early millions of years, it struck hard, so hard that the outer layers are blasted away, ejected into space, leaving just the dense metallic interior. If that's true, and the evidence leans that way, then Mercury isn't just a small planet. It's the stripped core of something larger, a planetary phantom. And I think that's poignant, like gazing at the scar tissue of the solar system. But it's not just the structure, right? The surface itself narrates a story. It's covered, utterly blanketed in impact craters. You see, without an atmosphere for protection or significant geological activity to renew the surface, every collision, every tiny rock that hit it over the last 4 billion years has left a mark. So when you look at Mercury, you're seeing a surface that's like a time capsule. Some of those craters are ancient, truly ancient, dating back to the period we call the late heavy bombardment, when the inner solar system was pummeled by debris hurled from farther out. That phase left scars on all the inner planets, of course, but on Mercury they've endured. They're still there. But it's not just dead rock. That's the point. For a long time, people thought Mercury was geologically dead from the beginning. But as we started getting real data, especially from the Messenger spacecraft, you begin to see otherwise. Vast plains, smooth areas that aren't just impact ejecta, but volcanic, enormous lava flows. And that's crucial because it means Mercury was once active. It had magma, eruptions, heat, and then there are these cliffs, huge towering scarps, stretching for hundreds of kilometers across the surface. They're the result of contraction. The planet, as it cooled, shrank. The metallic interior solidified, and as it did, it pulled the crust inward, cracking and buckling it like dried mud. You don't see that on the other planets, not in the same way. It's as if Mercury is still settling into its final form. Now, something else, and this is important, is the question of atmosphere or the lack thereof, because Mercury has almost none. Not zero technically, but what it has isn't an atmosphere in the traditional sense. It's an exosphere, a very thin cloud of atoms blasted off the surface by solar radiation and micrometeoroid impacts. And because it's so tenuous, it can't retain heat. So on Mercury, temperatures are extreme. During the day, the sun is 7 times brighter than on Earth, and the surface can reach 430 degrees C. But at night, without any insulation, it drops to minus 180. That's a swing of over 600 degrees. And I think that's fascinating because it illustrates how vital an atmosphere is not just for life, but for temperature regulation, stability, erosion, even for shaping the surface. On Mercury, there's no wind, no rain, no water, just bare rock exposed for billions of years. And that provides something rare, a record that hasn't been erased. There's also the matter of magnetism. You wouldn't expect a small planet like Mercury to have a magnetic field. And yet it does. A weak one, about 1% the strength of Earth's, but present. And that reveals something significant. It means that despite its size, Mercury's core is at least partially molten, still churning, still conducting electricity, which is surprising because small planets tend to cool quickly. They solidify. But here something has kept part of that core liquid, perhaps the presence of sulfur lowering the melting point or something we haven't fully figured out yet. And then there's the question of water. Not on the surface, of course, it's far too hot for that. But in the polar regions, in the deep, permanently shadowed craters near the poles, radar data suggests there's ice, actual water ice, stable, tucked away in eternal darkness, which, if you think about it, is astonishing. The planet closest to the sun harboring pockets of frozen water. So when you piece it all together, what you get is a world far more complex than it first seems. Not just a burnt out cinder, not just a dead ball of iron and stone, but a place with a history, a planet that's endured fire and impacts, eruptions, and contraction, and somehow still holds a magnetic heart. It's quiet now, yes, and geologically mostly inactive, but its past is inscribed in the crust, the plains, the scars, and in a very real physical sense. Mercury embodies an untraveled path. It could have been something larger. It might have grown bigger, retained more crust, developed an atmosphere, perhaps even surface water. But instead, it became what it is, a bare, scarred world, orbiting close to the furnace, locked in a slow rotation, spinning 3 times for every 2 orbits. That's another oddity, by the way. Its day from sunrise to sunrise is longer than its year, 176 Earth days. A consequence of this resonance between rotation and orbit, and it creates strange effects. Tidal interactions, thermal stresses. It's a system balanced on peculiar ratios, and I think that illustrates more than anything that the paths of these planets aren't inevitable. They're contingent, dependent on collisions, timing, proximity to the sun, interactions of fields and materials. Mercury, in a way, is an exploration of limits. The limit of how close a planet can orbit and survive. The limit of how small a world can be and still hold a magnetic field. The limit of planetary endurance, and yet it's there, after billions of years, enduring, silent, scorched, scarred, but resilient, a testament to the chaos and violence of planetary birth and the strange, enduring stability that sometimes emerges from it. Venus, well, it's peculiar, isn't it? Extremely peculiar. From a distance, you might think at first glance that it's Earth's sister, similar size, mass, position in the solar system, just a bit closer to the sun. And yet, it couldn't be more different. It's like looking in a mirror and seeing not yourself, but something distorted, familiar, and alien at once. Captivating, truly enigmatic, is that they likely started the same way. You'd expect them to be, if not identical, at least alike. But something happened, something subtle early on, and that tiny difference was enough to send Venus down an entirely different evolutionary path. And now it's the hottest planet in the solar system, hotter even than Mercury, despite being nearly twice as far from the sun. That's unexpected, right? Counterintuitive. You'd think the closer to the sun, the hotter. But here the atmosphere intervenes. Venus has an atmosphere, but not just any atmosphere. A monster, thick, suffocating blanket of carbon dioxide, over 90 times denser than Earth's, like walking under a kilometer of ocean. The pressure is that intense, and that gas traps heat. It lets in sunlight but doesn't let out infrared radiation. So the temperature builds and builds until the whole planet becomes a furnace. Surface temperatures around 470 Q, hot enough to melt lead, and it persists day and night, equator or poles. Just heat, relentless, crushing heat. But it probably didn't start that way. That's the thing. Venus might have had oceans once, might have had water, clouds, perhaps even rain. Imagine a younger sun, a slightly cooler planet, an atmosphere not yet poisoned by carbon dioxide. But then something tipped. Perhaps the oceans evaporated slowly over time, and when water vapor rises into the atmosphere, it's a greenhouse gas too. That kickstarts warming. And the warmer it gets, the more water evaporates. It's a feedback loop, a runaway process. Eventually, the heat becomes strong enough to break apart water molecules. Ultraviolet from the sun strips away hydrogen, and it escapes into space. Without hydrogen, there's no water. And without water, there's no regulation, no way to lock carbon into rocks, no gas cycles. Carbon dioxide accumulates, and the greenhouse effect turns catastrophic. That's what we mean by a runaway greenhouse effect. Not gradual warming, planetary transformation. Now, the surface, well, it's dramatic. There are volcanoes, not a few, but thousands, some absolutely gigantic, hundreds of kilometers wide, massive shield volcanoes that dwarf anything on Earth. There are vast plains of solidified lava, oceans of rock that once flowed across the landscape. And strangely, we don't see many craters, which means the surface is young. Not in a human sense, but geologically young, perhaps 500 million years old. That suggests something dramatic. Some resurfacing event, possibly a global volcanic episode or a slow planetary crustal overturn. But whatever it was, it erased the record of an older surface, reset the clock. Also, the question of whether volcanoes are still active, whether Venus is geologically alive. And evidence is mounting. There are transient hotspots, small variations in thermal emission, hints of gas, spikes in sulfur dioxide in the upper atmosphere. These things suggest the planet's interior isn't cold, it's still stirring, breathing in some way, and then the winds. Venus has this bizarre super rotating atmosphere. The surface rotates incredibly slowly. One Venusian day is longer than its year, over 240 Earth days. But the atmosphere, the upper cloud layers, whips around the planet in 4 days, hundreds of kilometers per hour. Captivating, and we don't fully understand how it works, how such a differential arises, such a mismatch between surface and clouds, a puzzle. And regarding rotation, it's retrograde, it spins backward. Almost no other planet does that. You'd expect slow prograde rotation, if anything, but Venus is either flipped or perhaps always was, though hard to believe. Maybe it was hit early by something massive, tilting or slowing it to a stop, then sending it back. Or tidal interactions with the sun gradually overturned the rotation. We don't know for sure. But whatever the cause, the result is a planet with an extremely slow retrograde rotation and an incredibly fast swirling atmosphere. And the clouds are thick, yellowish, laden with droplets of sulfuric acid, not water. No water. The entire cloud system is acidic, incredibly hostile. And yet there's an idea, a hypothesis, that perhaps in the upper atmosphere around 50 kilometers up, where pressure and temperature aren't so extreme, you might find something, some chemistry, something unusual. Strange signatures have been detected, spectral lines hinting at phosphine, which on Earth is associated with biological activity. That caused a stir. But follow-up observations are ambiguous. Some see it, some don't. Not settled, but it reminds us that even the most hostile environments can surprise. And if you think about it, truly think, Venus is a warning, a vision of what a planet like Earth could become under the wrong conditions. A shift too far in one direction, an imbalance in greenhouse gases, loss of water, breakdown of regulation, and you get this, a world unrecognizable, a place where the surface is hot enough to melt metal, the air toxic, the pressure crushing, and yet so close, right there. You can see it in the sky shining brightly in the morning or evening, and you wouldn't guess. You wouldn't imagine what's beneath the clouds. So when we speak of Earth and Venus as sisters, it's not poetic license, literally. They're twins, born from the same disk of dust and stone, built from the same materials in the same place, but one veered left, one right, one retained oceans, a temperate sky, while the other spiraled into heat and death. And that raises a host of questions, doesn't it? Questions about planetary stability, habitability, thresholds. How finely tuned does a planet need to be to remain Earth-like? How close to the sun can you be and hold on to water, life? How much is chance, collision, timing, solar output, orbital parameters? Venus shows that being in the so-called habitable zone guarantees nothing. No promise, just a starting point. And yet, despite everything, it's a world of profound scientific interest, because understanding what went wrong on Venus helps us grasp what went right on Earth. We can compare, model, seek divergence points, moments when paths split, and perhaps it says something about how to safeguard what we have here. It also aids in looking outward to exoplanets, other systems, because when we detect a rocky planet around another star that seems Earth-like in size and mass, we can't assume it's another Earth. It might be another Venus, shrouded in clouds, baked in heat. A twin, yes, but dangerous. A reminder that appearances can deceive, and maybe the true message from Venus is that beneath a familiar form, under similar mass and gravity in orbit, something entirely alien might lurk. A world that started like ours, but now stands as a monument to what happens when planetary forces spiral out of control. Not through something sinister, not by design, but through physics. Just physics. Atmospheric chemistry, radiative transfer, orbital mechanics, blind laws of nature, playing out, crafting something extraordinary, something that could have been blue and temperate, but is now lost in perpetual yellow haze. Earth's story is different, isn't it? It's not just another rocky planet orbiting a star. It's the one, the only one we know that developed life, complex life, intelligent life. But before all that, before oceans, forests, cities, and the rest, it was just another world forming from the same material, the same dust and rocks in the inner disk. And it's strange, truly strange, how everything had to align for Earth to become what it is. Because in those early days, it wasn't clear this place would be special. So imagine it about 4.5 billion years ago. A young, glowing world still accreting material. Collisions happening constantly. Giant impacts. The surface molten, mostly a magma ocean, and it grows slowly at first, then rapidly as more and more planetesimals and embryos crash into it. One of those impacts, perhaps the biggest, with a body we call Theia, Mars-sized or so. And that collision wasn't a kiss. It was head-on, catastrophic. It tore off a chunk of the planet, ripped part of the mantle and flung it into orbit, and from those debris, the moon formed. And that's important, not just for tides or romance. The moon stabilizes Earth's tilt, slows our rotation, alters the planet's evolution. Without it, our axis might wobble chaotically. Seasons would vary wildly, climate unstable. Life might be impossible. So that one impact, that single brutal event, might be one of the most decisive in the history of life on Earth. And yet random, pure chance. Timing, trajectory, mass. Once things settled, relatively, the surface began to cool. Magma solidified into crust, thin and fragile at first. The atmosphere, still thick with carbon dioxide, water vapor, and nitrogen, started to settle. And here's the thing. Water didn't just appear. It condensed from vapor in the air. Rain fell for thousands of years, filling basins, carving the crust. Oceans didn't arrive all at once. They accumulated, and with them came weather, erosion, cycles. Now at this stage, you've got a planet with a rocky surface, liquid water oceans, and an atmosphere, but that atmosphere wasn't breathable, not even close, toxic by our standards, Mostly CO2, some nitrogen, traces of other gases. No oxygen, not yet. That came later, much later. But the planet was ready, conditions in place. And in those oceans, in the deep mineral rich water near hydrothermal vents, or perhaps in shallow pools, chemistry began to shift. Molecules started to organize, replicate. Not clear where or how. Several hypotheses, but eventually the first life emerged. And from that moment, Earth became different because life began interacting with the planet. It wasn't shaped solely by geology anymore. It started shaping geology. Early microbes began absorbing and emitting gases. Some produced methane, some started photosynthesizing. Not the oxygen kind, not yet. But slowly, step by step, the biosphere built up. And eventually, probably about 2.5 billion years ago, something extraordinary happened. Cyanobacteria evolved a version of photosynthesis that produced oxygen, free oxygen. At first, a waste product, but it accumulated slowly, and that began a new era, called the Great Oxidation. It didn't happen overnight. It stretched over hundreds of millions of years. But eventually, the atmosphere's composition changed. Oxygen reacted with iron in the oceans, forming rust that settled to the bottom. You can still see those deposits. Banded iron formations scattered across ancient lands, relics of that time. And once the iron was saturated, oxygen began building in the air. And that changed everything, because oxygen provides energy, the most efficient electron acceptor in biological systems. With it, organisms could grow larger, more complex. Multicellularity became possible, nervous systems, movement, and that eventually led to animals. But we're rushing ahead. Before that, the planet itself was changing. Tectonic plates, driven by heat from the interior, began to shift. The crust cracked, recycled, collided. Continents formed, broke apart, drifted. There were supercontinents, Rodinia, Pangaea, vast land masses that shaped climate, rains, even ocean currents. And with each shift came new environments, challenges, evolutionary paths. And climate fluctuated, sometimes wildly. There were ice ages, episodes of snowball Earth, where it's thought the whole planet might have frozen over, or nearly so. Temperatures plummeted. Glaciers crawled to the equator. Life nearly halted. And yet it endured, probably in pockets. Hydrothermal vents or under ice where light could penetrate. And when the planet thawed, life expanded, diversified. The Cambrian explosion, 500 million years ago, saw a sudden emergence of complex organisms with shells, limbs, eyes, and from there, the story accelerates. But all of it, oceans, continents, atmosphere, climate, rests on processes that began early: heat, water, chemistry, and the balance among them. That's what makes Earth exceptional. It's active, dynamic, self-regulating. There are feedback loops. When CO2 levels rise, weathering intensifies, drawing it out. When the planet cools, volcanic emissions restore balance, not perfectly. Fragile indeed, but sufficient. Enough to keep the planet in a range where life thrives, and not just surface processes. The magnetic field generated by the churning of molten iron in the core shields from solar radiation. Without it, the atmosphere could be stripped away like on Mars. But it's there, invisible but essential, deflecting charged particles, shaping auroras, and of course plate tectonics. Not just a geological curiosity. It recycles carbon, builds mountains, creates new crust, and may be key to long-term habitability. Most planets lack it. It requires the right amount of internal heat, crustal composition, perhaps water, to lubricate the plates. A delicate balance. So when we say Earth is special, It's not just because we're here, it's all these things: internal structure, surface processes, atmospheric evolution, magnetic protection. Everything aligned just right, and not once but sustained for billions of years. That's the hard part. That's the rare. Stability, resilience, and all of it. It all starts from the same materials as Mercury and Venus, the same dust, the same silicates, iron, but the sequence, timing, combination of events created something entirely different. A place with rain, rivers, forests, whales, a place with drifting continents, shifting climates, a place where chemistry became biology and biology rewrote chemistry. And now we're part of that story, not separate from it, not observers, products of billions of years of planetary evolution from collisions, volcanism, tectonics, photosynthesis, extinction, survival. No myth, no metaphor, physics, chemistry, time. And I think what makes Earth so extraordinary isn't just what it is now, it's what it went through to become this way, because nothing was guaranteed. It could have followed Mercury's path, cold, quiet, inert, or Venus's, hot, acidic, dead, but it didn't. Somehow, through the chaos of formation, the violence of impacts, the fragility of early life, it endured. And that changes how we see everything, because it means a planet isn't just a place, it's a process, a history. And Earth's history is still being written. There's something quietly awe-inspiring about what happened next. After all the chaos of formation, the impact that birthed the moon, the cooling of the surface, after oceans began to spread and life appeared in those deep, dark places under the waves, the planet didn't just settle. It didn't remain static. It began to change slowly, deeply, relentlessly. And that change flowed from inside out. The crust wasn't fixed. Continents weren't fixed. They started to move, shift, break, join. Over hundreds of millions of years, Earth's surface became a slow puzzle that never stays in place. And this ability to move, to reshape itself, sets Earth apart. You don't see it on Mercury or Venus. Not like this. Not on this scale, because Earth has plate tectonics. And that process, well, one of the great engines of planetary evolution. Not just geology, climate, biology, atmosphere. Everything's linked to it. Earth's crust isn't a single slab. It's broken into sections, plates, floating on the mantle below. And that mantle isn't rigid. It flows slowly, convecting over vast periods. Heat rises, cold sinks, and that motion pushes the plates. So continents drift, collide, rift apart, and when they crash, they crumple and rise, forming mountain ranges like the Himalayas, still growing. When they separate, rifts open, new crust forms at mid-ocean ridges, spreading very slowly, almost imperceptibly but constantly. And when one plate sinks under another subducts, it drags material deep into the mantle, melts it, and sometimes feeds volcanoes. That cycle of crust creation and destruction is part of how carbon moves across the planet. When volcanoes erupt, they release gases, including carbon dioxide, into the atmosphere. But that CO2 doesn't stay forever. It dissolves in rainwater, forms weak acids, weathers rocks. Those reactions pull carbon from the air, eventually washing it into oceans, where it can bury in sediments. And when those sediments subduct, carbon returns to the mantle, ready to emerge again someday. It's a long cycle, hundreds of millions of years. But a thermostat, a planetary thermostat, regulating climate on geological timescales. That's why Earth doesn't swing too far in one direction or another. Not permanently, at least. There were snowball and greenhouse episodes. Yes. But climate returns to temperate, habitable, and without tectonics, there'd be none of that. No erosion, weathering, mountain building. Earth must rise to be worn down. Carbon must be drawn out and sequestered. Balance, delicate, and not guaranteed. Venus doesn't do this. It has highlands, yes, and vast plains, but no active plate tectonics. Not like here. Mars either. It might have had something similar in the distant past, but now it's quiet, frozen. Earth is unique in this as far as we know. And this motion, the shifting of land masses, shaped life itself. When continents merge into supercontinents like Pangaea, you get massive interior deserts, monsoons on coasts, new evolutionary pressures. When they break up, they create barriers, oceans, mountains that isolate species, drive divergence. That's how biodiversity arises. That's how ecosystems evolve in parallel, adapting to different niches. Geography over time becomes biology, and then ice. Climate shifts and ice sheets grow. And as they grow, they draw water from oceans, lowering sea levels. When they melt, they flood coasts. These glacial cycles are tied to changes in Earth's orbit, tilt, axial wobble, called Milankovitch cycles, subtle celestial rhythms that alter how sunlight reaches the surface. And those shifts over tens and hundreds of thousands of years drove the advance and retreat of glaciers. You can see the traces left behind. U-shaped valleys, moraines, massive boulders dropped by melting ice. And these cold periods aren't just geological curiosities. They shaped evolution. Species had to adapt, migrate, retreat. Some went extinct, others thrived. Human evolution in particular was driven by these cycles. Climatic instability forced early hominids to become more adaptable, flexible, to move, migrate, innovate, change. The planet never stood still. Not the crust, not the climate, not life. Everything moved constantly. And over billions of years, life grew more complex. From microbes to multicellular organisms, from simple sea creatures to things with skeletons, shells, nervous systems, then to land plants, animals following, insects, amphibians, reptiles, eventually mammals. But the ground they walked on, the air they breathed, the oceans they swam in, all were shaped by deep, slow processes. Erosion carving river valleys, volcanoes building new land, ocean currents sculpted by continental positions, all one system. Even extinctions, those great mass die-offs, punctuating the fossil record route in these planetary processes. The Permian extinction, the worst in Earth's history, may have been triggered by massive volcanic eruptions in Siberia. They released huge volumes of greenhouse gases, warmed the climate, acidified oceans, collapsed ecosystems. The Cretaceous Paleogene extinction that wiped out dinosaurs was caused, or at least finished, by an asteroid impact. But even where it hit matters. The rock struck a sulfur-rich region, lofting aerosols into the upper atmosphere, blocking sunlight, cooling the planet. Darkness fell, plants died, herbivores, predators, chain reaction, and yet life persisted, altered but not ended. Because that's the story, I think. Not just catastrophe, but resilience. Not just destruction, but renewal. Continents broke and reformed. Climates warmed and froze. Species rose and fell. But the planet, this planet, endured. Not because it's stable, but because it changes, responds, adapts. Even now it still does. Continents drift. Plates grind against each other. Earthquakes shake the surface. Volcanoes reshape land, climate shifts, and we're part of that. Building cities on these plates, growing food in soils from ancient ash and sediments, breathing an atmosphere shaped by eons of volcanism and biology. But it all began so simply, just rock and dust and gas. And from that, somehow, we got a world of such complexity, dynamics, unpredictability, a world that never sits still, a world that reshapes itself every moment, a world where the past is buried in stone, layers, folds, fossil remnants waiting to be read, and all of it, every mountain, every ocean, every glacier, every grain of sand, all part of one long, slow, majestic process. And that process hasn't ended. A planet has a rhythm, a deep planetary heartbeat, if you will, something playing out over millions of years. Cycles, long, slow cycles of climate, ice, warmth, droughts and floods, expansion and collapse. They're invisible when you look out a window. Not obvious when you walk through a forest or stand by a river, but they're there beneath it all. This constant shifting of energy through time, shaping the land in ways hard to grasp unless you step back far. It's impressive how many of these cycles operate simultaneously. Of course, the carbon cycle, water, mountain building, but layered on them are glacial, interglacial, orbital variations, long-term tectonic rhythms that uplift continents, draw carbon, build towering mountains that then erode to dust. And everything's connected. That's the key. Not one system. Interlinked systems feeding off each other, influencing, responding. Take ice ages. Over the last few million years, Earth's climate has been dominated by these recurring glaciations, massive continental ice sheets advancing and retreating like slow tides, and not random, tied to changes in Earth's orbit, its eccentricity, axial tilt, precession. All these factors affect how much sunlight reaches the surface, especially at high latitudes. And when conditions align, when summer becomes too cool to melt winter snow, that snow starts accumulating year after year, compressing into ice, thick ice, kilometers deep. These glaciers advance slowly but powerfully. They scour the land, reshape valleys, crush forests, grind mountains to stubs, push rock and debris ahead, leaving ridges, moraines, great arcs of stone. And when they melt, when climate shifts again, water returns to oceans, sea levels rise, and the land rebounds slowly like a sponge, uncompressed. And that rebound lasts thousands of years. The weight of ice actually depresses the crust, and when it goes, the land rises. You can still see it in Scandinavia or Canada, where the land uplifts centimeters per century, still responding to the end of the last ice age. But the effect isn't just geological, it's biological. As ice advances, ecosystems collapse or migrate, species forced into refugia, small isolated pockets where they survive the cold. And as ice retreats, they expand again, reclaiming land. And in doing so, they change, evolve, adapt to new climates, terrains. That's one reason biodiversity is rich in post-glacial zones. They've gone through cycles of destruction and renewal time and again. And ice doesn't just shape land and life, it affects the atmosphere too. As glacial sheets grow, sea levels fall, exposing continental shelves. And that influences ocean currents, which in turn affect climate. Cold water sinks, warm rises, and that drives the global conveyor of currents, redistributing heat around the world. If the system is disrupted, if too much fresh water enters the oceans too quickly, it can shut down or slow dramatically. And that again alters climate, not gradually, but abruptly. We've seen it in the past. Events like the Younger Dryas, a sudden return to glacial conditions about 12,000 years ago, may have been caused by just such an interruption. So climate doesn't shift on its own. It responds to layers of feedbacks: ice and water, ocean and air, vegetation, clouds. A change in one part echoes through all. And fascinating how life learned to live within these patterns, or at least tries. Forests expand in warm periods, contract in cold, grasslands take over, Animals migrate, adapt, speciate. Some go extinct, others flourish, and this dynamism, the constant response to a changing world, drives complexity, not a static environment, always in motion, and life hangs on, but not everything adapts. Sometimes change is too fast or too extreme, then ecosystems break. We see it in the fossil record. Mass extinctions tied to sudden warmings or rapid coolings or shifts in ocean chemistry, sometimes volcanic, sometimes orbital, sometimes later us. And even in these longer cycles, there are smaller ones, seasonal shifts, droughts lasting decades, solar activity fluctuations, El Nino and La Nina events reshaping rains across continents, dust storms from Africa fertilizing the Amazon, fires shaping forests, clearing land, triggering germination in species adapted to heat and flame. The biosphere is constantly tested, stretched, molded by these forces, and over time it grows more complex. Life learns to harness change. Some species become generalists, able to survive in multiple conditions. Others highly specialized, thriving only in narrow niches, but evolving quickly, filling gaps from the last big disturbance. And not just animals and plants. Microbes respond too. In fact, often lead in soils, oceans, deep ice cores. Communities of bacteria and archaea shift composition with climate, influence nitrogen cycles, methane emissions, cloud formation, invisible drivers of change. And as these cycles play out, you start to see structure, ecosystems, relationships between organisms beyond competition, symbiosis, predation, mutualism. It's a web, not a ladder. And rooted in geology, geography, the climatic history of the land beneath. That's why rainforests are where they are. Why deserts form where they must. Not arbitrary, the result of millions of years of weathering, uplift, rain shadow effects, orbital forcing. The Amazon, for example, sits on ancient sediments, weathered from the Andes. Winds carry moisture from the Atlantic. Trees themselves help pump water into the atmosphere. And it's all feedback. Lose too many trees, the system breaks, rain stops, forest collapses. Not prophecy. It happened before, so you understand Earth's surface isn't just a stage. It's a participant, changing, and changed by the things living on it. Deep interplay between lithosphere, atmosphere, hydrosphere, biosphere. Not four separate systems, one dynamic breathing whole. And if you drill back through layers of rock, you can read it. Shifts in isotope ratios, sudden appearances of certain fossils, extinction layers, volcanic ash. Every centimeter of sediment, a snapshot, a fragment of planetary history. And when you assemble it all, you get a picture of incredible resilience, but also incredible fragility. Because Earth, for all its power, is also precarious. These cycles maintain balance, but they can tip. Feedbacks can overwhelm. Push too much CO2 too fast, and weathering reactions can't keep up. If ice melts too quickly, reflective surface vanishes. Planet warms more. If oceans warm, they release stored gases, methane, CO2, making it worse. It happened before. The Paleocene-Eocene thermal maximum about 56 million years ago. A sudden spike in global temperatures, likely from massive methane release. Oceans acidified. Some ecosystems collapsed, but life survived. Adapted, found a way through. That's the pattern. Catastrophe followed by renewal. And perhaps most impressive, all this, climates, currents, ice, life, isn't static. It changed all the time, long before humans, long before forests or dinosaurs, or even complex cells. Earth was always shifting, cycling, adjusting. And despite all the turbulence, it remained habitable. Through all the swings, something kept the planet within life's bounds. Not too hot, not too cold, not too dry or acidic. Just stable enough, long enough, for life to become what it is now. And that's not just luck, it's process, cycles, these long, slow, grinding rhythms that keep the planet breathing. Not perfectly, not eternally, but sufficiently. And we're now part of that system, not above it, not outside it, within. Another feedback, another force shaping the future. Like ice, volcanoes, winds, part of the rhythm, part of the change. It's truly striking when you look at the three of them, Mercury, Venus, and Earth, and realize they all began in the same place, the same disk of dust and gas, the same early conditions, the same origins, and yet ended up so differently, wildly differently, not just size or distance from the sun, deeper. What happened afterward? How they evolved, how they responded to impacts, internal heat, atmosphere, time. That divergence, that branching of fates, says something profound about how planets work, how fragile conditions are, and how easily it could have gone otherwise. Mercury, the closest, ended up as metallic remnants, a planetary core really orbiting through a furnace of radiation and quiet now, cold, motionless, no plate tectonics or oceans or breathable atmosphere, just a silent cratered surface reflecting a history of violent past, not changing much more. Done. Geologically, a world fossil. Venus took another path, not quiet, not cold, but smothered, overheated. Atmosphere turned against it. No water anymore. Nothing of rivers, rain, just a dense shroud of carbon dioxide and sulfuric acid, heat trapper warning, and surface remade by lava, volcanoes on a grand scale, but not active like on Earth, no drifting plates or turbulent oceans, stuck under pressure, volcanic stagnation, if you will. Heat can't easily escape, and it builds, and now locked in a runaway state. Then Earth in the middle, the one that found balance not by design, but through timing, position, perhaps even luck. The right amount of water, the right collisions, magnetic field, plate tectonics, and most importantly, the ability to change and keep changing in a way that sustains life, living surface, breathing system, and the only one we know. Impressive that the raw ingredients these planets are made of aren't too different. Silicon, iron, oxygen, magnesium, all there in similar proportions more or less. It's the processes, the history that make the difference. Mercury lost its outer layers, Venus lost its oceans, Earth didn't. And those differences accumulate over time like forks in the road. And you start to wonder, what if? What if Mercury hadn't endured that massive impact? Would it be larger, retained an atmosphere? Or perhaps ice in shadowed craters, more widespread, more stable? Could it have sustained activity longer? Maybe, but we'll never know. And Venus? What if the early climate had stayed a bit cooler? If oceans had lasted a little longer? Water, after all, plays a key role in climate regulation. Dissolves carbon dioxide, keeps surface temperatures in check, drives plate tectonics, lubricates the crust. If that water had remained, if it hadn't boiled away, could Venus have ended up like Earth with water clouds instead of sulfuric acid, with continents, rain, oceans, life? Possibly, very possibly. But once it tipped, irreversibly. The greenhouse effect fed itself, and the rest locked in. You get a sense that these planets are examples of divergent outcomes, case studies. What happens when you tweak parameters, when initial conditions shift a bit? A few percent closer to the sun, a few million years earlier or later, for a big impact, a different gas mix, and suddenly you're on a path to a lifeless rock or hellish heat or perhaps blue-green oceans and continents. But not just internal processes, time too. Time matters because even Earth could have changed, did change. For most of its history, there was no complex life, just microbes quietly cycling chemicals in the sea. Billions of years without oxygen, land plants, animals, that's the baseline. Default, complex, multicellular, intelligent life is rare, not because impossible, but because it takes so long and depends on stability, on not being wiped out, not tipping too far one way or the other. And looking at the three, you realize Earth walked a knife's edge, the right amount of carbon in crust and atmosphere, the right balance between volcanism and weathering, the right magnetic field to protect the surface from solar wind, and the moon. Don't forget, the moon, large enough to stabilize axial tilt, keep seasons regular, slow rotation to a manageable speed. Pull any lever too far, and the result isn't Earth. So these planets aren't just neighbors, connected chapters in a shared history, and yet they embody three utterly different outcomes, three very different experiments, if you will, in planetary evolution. One ended in silence, one in fire, one in life. And that says something powerful, because when we search for other worlds around other stars, find rocky planets and habitable zones orbiting distant suns, we must remember that being in the right place isn't enough. Starting point, nothing more. Because habitability isn't just distance, history, retention, regulation. A planet must hold volatiles, recycle carbon, avoid the worst impacts, tidal locking, runaway feedbacks. It needs time, long, quiet time for life to emerge, stabilize, flourish. That's what Earth had, not because chosen, but because lucky or perhaps just fortuitously fell into the right patterns. And that makes Mercury and Venus incredibly valuable because they show what goes wrong, show the boundaries of the stable zone, the limits of planetary success, and remind that even small changes, tiny shifts in chemistry, temperature, timing, can lead to vastly different futures. There's also something almost poetic. These three planets born from the same material, forged in the same fire, destined for utterly different fates. One stripped bare, one suffocated, one surviving. And you realize survival, the emergence of life, isn't default, not a natural outcome, the exception. And yet we're here on the one that worked. Looking back, studying the others, asking what might have been, like a family of worlds, each bearing the marks of its path. Some silent, some screaming, some singing with ocean's weather, life. All from one beginning, one disk of dust and fire. And more than that, their stories aren't finished. Even Mercury, seemingly dead, may shift from tidal stresses, respond to the sun's pull. Venus may rumble occasionally with volcanic flows. Earth, of course, continues to evolve. Continents shift, ice caps grow and shrink, life adapts, climate changes. It's all still happening. And here's the real thing. These aren't static worlds. Dynamic processes, not just balls of rock in orbit around a star, but open systems, changeable, responsive. And when you see them that way, not as finished products, but as unfolding stories, you see differently. You see the fragility of it all, the delicacy of maintaining balance, the razor's edge separating a habitable world from a hostile one. So when you stand on Earth and feel the wind, look at the clouds, walk continents that moved for hundreds of millions of years, you're witnessing something rare. Not because Earth is the only place it could happen, but because one of the few where it did. And if that doesn't make you pause for a moment, then maybe look at Venus again, at Mercury. Remember, they too were worlds of possibility, worlds that, under different circumstances, might have been something more. something like this, but weren't. Couldn't because the universe doesn't favor life. It allows it sometimes under the right conditions, at the right time on the right kind of world. There's an idea that once a planet cools, once it stops moving, internal flow, then it's done. Evolution complete. But that's not entirely true, is it? Not fully. Because even in stillness, even without motion, you can read the history, see in a world's silence the echo of all it was. Mercury, for example, geologically inert. Yes, but still holds the memory of ancient impacts, frozen ridges, contraction of a once molten world into itself. And Venus isn't frozen, stagnant. It boiled over and stopped, held under a crushing sky. Heat trapped beneath clouds that no longer cleanse. Still some energy, just contained. Contained in a system that doesn't reset. And Earth persisted, not smoothly, not predictably, but moved. And that motion, that instability, became a cradle for something extraordinary, complex. Because the planet didn't just evolve geologically, it evolved biologically, became a biosphere, an intertwined network of life forms and processes feeding off each other. And that biosphere didn't stay simple. It changed, diversified, responded. Strange to think about the transition from simple chemistry to complex ecosystems. At first just cells, single cells floating in oceans, dividing, feeding, sometimes forming colonies. But those cells over time began to cooperate, specialize, and that cooperation, the emergence of multicellular life, wasn't inevitable, not encoded in physics, again contingent. It happened because the environment allowed, because oxygen levels reached a threshold, because temperatures stable enough time without catastrophe, and once life became multicellular, the pace quickened. Limbs, eyes, jaws, backbones, all exploring new ways of being, and eventually came to land. Plants, first simple like mosses, then vascular with roots and stems, drawing nutrients from soil, transforming the atmosphere further. And then animals followed. First invertebrates, arthropods scuttling coastlines, and later vertebrates, crawling from swamps, adapting to air, sunlight, dry ground. And over hundreds of millions of years, ecosystems formed. Forests, reefs, swamps, deserts, all finely tuned to local climate, soil, sunlight. Species scattered into every niche. Some evolved to climb, swim, hunt in packs, or burrow underground or fly. Great branching, explosion of forms. And all powered by energy from the sun, captured by plants, passed through food chains, recycled by decay. Nothing wasted, everything connected. But not just a tangle of biology, information. That's the part that feels eerily profound. Life doesn't just persist, it remembers, encodes strategies, DNA, memory, molecular record of all that worked in the past, every successful adaptation stored, refined, passed on, and every extinction, every ecological shift pressures that code. Not consciously, not directed, but responding, learning slowly, blindly, but learning. And as ecosystems grew more complex, behavior did too. Animals began to recognize patterns, solve problems, and some started to think, not just react, but reflect, store experiences, not just genetically, but through memory, through brains, and from those first sparks of neural activity. Eventually emerged intelligence, not once, but several times. You see it in cephalopods, birds, mammals, different solutions to the same problem, how to survive in a dynamic, in a unpredictable world. And then sometime very recently, cosmically, a certain line of primates began using tools, fire, language, abstract thought. And those innovations changed everything, because for the first time a species could not just adapt, but shape the environment. alter, dominate, right upon it. And here we are, life aware of itself, its place, its planet, that knows about tectonics, evolution, ice ages, star formation. A species capable of reflecting on the system that created it, sustained it, capable of building cities, sequencing genomes, launching machines into orbit, into deep space, to look back and peer ahead. But it didn't happen in a vacuum. It happened here on this world. This particular world, with particular composition, orbit, balance of feedbacks. And that's important because Earth didn't just produce life. It produced complexity, intelligence, culture, technology, and that progress isn't inevitable, not guaranteed, but permitted. Conditions didn't forbid it, and in that sense, Earth stands alone. Mercury had no chance, Venus neither. Their windows closed early, too early for life to establish or perhaps survive, too hot, too cold, too unstable. And the result? Silence. No symphony of biology thought, just geology. One path, but Earth shows another. Shows the possible when everything goes right, when a planet stabilizes long enough, when systems feed back gently, not destructively, when volcanism, weathering, solar input, biosphere sit in a range, narrow but sufficient for life to persist. And the biosphere we see now with whales, bees, fungi, forests, isn't static. Never was. Species evolve, go extinct, emerge, ecosystems shift, climates oscillate, polar caps grow and shrink, deserts migrate, forests burn and regrow, coral reefs rise and collapse. But through it all, the biosphere maintains balance. Not perfect, not precise, but resilient, flexible, able to absorb change up to a point. And that's where it becomes fragile, because the system sustaining life, resilience, aren't infinite. They have thresholds. And if you push too far, if oceans acidify beyond a certain level, or temperatures rise too quickly, or key species vanish, the system can unravel, not all at once, but in cascades. Interactions break, chains collapse, niches go unfilled, and resilience yields to fragility, stability to unpredictability. And strange, perhaps humbling, that this isn't a new idea. The planet has seen collapses before, many times. Mass extinctions, sudden losses of diversity. The biosphere recovered slowly, painfully over millions of years. Each time rebuilt, but differently. The past doesn't return. Those same forms don't evolve again. Evolution doesn't repeat exactly. It improvises, experiments, but doesn't undo. And that says something else, that once complexity is lost, it's not easy to regain. Diversity, as it thins, doesn't just bounce back to a prior state. It finds new paths, adjusts, and that's fine biologically, but may not include us. Because despite all our technology, knowledge, we're still part of the system. Rely on pollinators, fresh water, predictable seasons. Crops evolved under specific climates. Oceans not too acidic. Forests sequestering carbon. We're not separate from the biosphere, an expression of it, an extension. And so ultimately, looking at these three worlds, you see not three planets, three outcomes. One where geological evolution ended early. One where atmospheric instability locked the planet in perpetual heat. And one where everything just held long enough for life to emerge, complexity to rise, intelligence to reflect. And you start to understand planets aren't just physical objects, possibilities, canvases on which time paints with chemistry, energy, chance, structure. And from that, if the timing's right, you get not just rocks and minerals, but ecosystems, meaning perhaps even consciousness. And that's what makes Earth distinct. Not the materials, not the mass, but what it became, what it allowed, what it still allows. A world that didn't stop, didn't spiral into silence or flame, but turned toward complexity, toward life. Three worlds born from the same dust took different paths. One silenced by impact, one consumed by heat, and one that found balance. Earth became a cradle for complexity, thought, not fate, but chance. And in that fragile stability, life emerged and wondered why it alone succeeded.